In this video, the analysis of two-dimensional trusses is presented. This video covers an introduction, element equation of plane trusses and the corresponding example, a strain displacement matrix and the corresponding example, and two exercises for you. By the end of this video, you'll confidently analyze 2D trusses on your own. The goal here is to analyze two-dimensional truss systems or plane trusses by finite element method. The governing equation for the truss element in one dimension was presented in the part 2 of finite element series at Merzad Engineering. Plane or planar trusses are widely used in structural engineering due to their lightweight, high strength, and simple construction. They consist of two force members connected at nodes. Trusses are formed using triangular arrangement of bars which provide stability. Bridge and roof trusses are particularly common and have been constructed continuously from the past to the present. Here you can see a Parker bridge truss and a fan roof truss. To derive element equation of plane trusses, we could extend the element equation for one-dimensional systems. Also, we need an element equation in the global coordinate systems. As a result, the element equation can be assembled now into a global system of equations for the structure. To achieve this, we require the transformation of displacement and force vectors in two dimensions. For this purpose, first of all, we want to transform the component of vector u from xy coordinate system into x prime, y prime coordinate system. To find u prime x, we could project ux and uy onto axis x prime using cosine theta and sine theta. And then we have this relation u prime x equals ux cosine theta plus uy sine theta. We could do the same for finding u prime y. In fact, for finding u prime y, we could project ux and uy using sine and cosine theta onto the axis y prime. And now we could write these two equations into a matrix format. In the left side, we have u prime x and u prime y, and on the right side, we have a multiplication of a square matrix including cosine and sine of theta, and ux and uy components of u in xy coordinate system. To find a relation between u prime e and ue, which are the element nodal displacement in local coordinate system and in global coordinate system, first of all, we define the global coordinate system of xy and local coordinate system of x prime, y prime, and the theta e, which is the angle between these two coordinate systems. Then here we have nodal values for displacement and force in local coordinate system for a truss element in two dimensions. Here the parameter is indicated by a prime. Also, we know that f prime 1y and f prime 2y, which are the force component in y prime axis, must be equal to 0, then the equilibrium is met. Also here in this figure, we have nodal values for displacement and force in global coordinate system for a truss element in 2 dimensions. Then we could write the relations between the component of u prime e and ue by the application of these two equations into the node 1 and node 2. Then we have these 4 equations, and we could write these equations in a matrix format. On the left side, we have the component of displacement in local coordinate system, and on the right side, we have the component of displacement in global coordinate system. What connects these two displacement matrices together is called rotation matrix. In fact, now we have u prime e is equal to re multiplied by u, where re is called rotation matrix, consists of cosine theta e and sine theta e. In the equation u prime e is equal to re multiplied by ue, as we mentioned, u prime e is the element nodal displacement matrix in the local coordinate system. ue is the element nodal displacement matrix in the global coordinate system, and re is the rotation matrix, which is an orthogonal matrix. That is, re inverse is equal to re transpose, and we can write re transpose re is equal to re transpose, that is equal to the identity matrix of I. The same equation can be applied to the element nodal forces, and we can write f prime e is equal to re multiplied by fe, where f prime e is the element nodal force matrix in the local coordinate system, fe is the element nodal force matrix in the global coordinate system, and re is the rotation matrix, consists of cosine and sine of theta e. Additionally, we can write ue is equal to re transpose multiplied by u prime e, and fe is equal to re transpose multiplied by f prime e. In the next stage, we want to find the augmented element equation in the local coordinate system. We know that f prime 1y and f prime 2y must be equal to 0, then the equilibrium is met. For this purpose, we can use the element equation for 1 dimension, as we have found this equation previously in part 2. And then we could add zeros to the rows and columns corresponding to the f prime 1y and f prime 2y. And then we have this equation that relates nodal forces to the nodal displacement in the local coordinate system. And we have f prime e is equal to k prime e multiplied by u prime e. However, we cannot use this equation and assemble the element equation in local coordinate system to find the system of equation for the structure, because we need an equation for the element with the same direction of nodal displacement and forces. Then we could assemble those equations in the global coordinate system to find the global system of equation for the structure. Finally, the truss element equation in the global coordinate system can be derived by using this equation. F is equal to Re transpose multiplied by F prime E. Instead of F prime E, we could write K prime E, U prime E. Instead of U prime E, we could write REUE. At this point, the multiplication of three matrices of Re transpose K prime E Re is defined as Ke matrix. And now we could write Fe is equal to Ke multiplied by Ue. This is the element equation for 2D trusses. In this equation, the matrix Fe is the element nodal force matrix. In the global coordinate system, the matrix UE is the element nodal displacement matrix in the global coordinate system, and the matrix KE is the stiffness matrix in the global coordinate system. The stiffness matrix for the element can be achieved by the multiplication of Re transpose K prime E Re. We have the result here. In this matrix, the parameter Ke is axial stiffness of the element, the multiplication of cross-sectional area of the element, elastic modulus of the element divided by length of the element. Here C represents cosine of theta E and S represent sine of theta E. And using this equation, the element equation for the element in the global coordinate system, we have the element equation for the members that can be assembled in a system of equation for the structure. Now we want to solve an example. In this example, we want to determine the nodal displacements and reactions for the two-bar truss shown below. Both bars have a cross-sectional area of A and an elastic modulus of E. This is the uh, truss we want to analyze. This truss is under a vertical force of P at this point, and we have the dimension here. For the solution, first of all, we need to divide the structures into finite element and assign numbers to the nodes and elements. Here we have two members. We number the element as element number 1 and element number 2, and also we assign the numbers to the nodes, node number 1, node number 2, and node number 3. Then in the second step, we develop the elements stiffness matrices. This is the element stiffness matrix in the global coordinate system. For element number 1, the cross-sectional area is A, elastic modulus is E, and the length of this element is 4L. Theta is equal to 0. At node 1 of this element, we have the global node number of 1, and at node 2 of this element, we have the global node number of 3. We could substitute these parameters into this matrix to find the stiffness matrix for the element number 1 in the global coordinate system. On top and beside of this matrix, I wrote the degrees of freedom based on the global node numbers. That helps us when we want to assemble the elements stiffness matrices to find the uh, stiffness matrix for the structure. For the element number 2, the cross-sectional area is A, elastic modulus is E, and the length of this element is 5L. Theta is 150. At node 1 of this element, we have the global node number of 3. At node 2 of this element, we have the global node number of 2. And using these parameters, we could find the a stiffness matrix for element number 2 in the global coordinate system. Again, on top and beside of this matrix, I wrote the degrees of freedom related to the nodes of this element based on the global node numbers that could help us when we want to assemble this element stiffness matrix into the stiffness matrix of the structure. In the next step, we want to assemble the elements stiffness matrices and establish the global force and displacement matrices. The governing system of equations for the structure has a general form of Ku is equal to F, where K is the stiffness matrix for the structure, U is the displacement matrix for the structure, and F is the external force matrix for the structure. In this figure, we have unknown variables at node 1 and node 2. Reactions in x and y directions are unknown. At node 3, displacement in x and y directions are unknown. First of all, we assemble the stiffness matrix for the structure using the elements stiffness matrices in the global coordinate system, and based on the global node numbers and the related degrees of freedom in x and y direction. After that, we establish the displacement matrix for the structure at node 1 and 2. Displacement in x and y direction are equal to 0. At node 3, displacement in x and y directions are unknown. We are going to find them. Then we establish the global uh, force matrix or external force matrix for the structure at node 1 and 2. Reactions in x and y directions are unknown. We are going to find them. At node 3, external force in x direction is equal to 0 and in y direction is equal to minus p. In step 4, we solve the system of equations for the structure. For solving the system of equation, we could use trivial equations. In this method, we replace the equations corresponding to the degrees of freedom with known displacement by trivial equations. It can be done by assigning ones to the diagonal entries of the stiffness matrix, and also we need to assign zeros to the other corresponding entries uh, in the stiffness matrix. Also, we need to replace the corresponding entries in the external force matrix by those known displacement. After that, we have a reduced system of equation to solve, and after solving these two equations, we could find u3x and u3y. And after that, when the displacement matrix is known, we could find the reactions. As I explained, first of all, we need to solve this system of equations to find unknown displacement component in node 3. After having u3x and u3y, we could find the reactions in node 1 and node 2. It can be done by the multiplication of this part of stiffness matrix by displacement matrix to have the reactions in x and y direction for node 1 and node 2, and it completes the solution. Now we want to derive the strain displacement matrix, which is needed in the post-processing step. In fact, in finite element analysis, strain and stress are computed during the post-processing step using nodal displacement. For this purpose, the strain displacement matrix is required, which is derived from the strain definition. Here we have the normal strain definition, delta u prime divided by LE. Delta u prime can be written as u prime 2x minus u prime 1x. This expression can be obtained by the multiplication of a row matrix of minus 1, 0, 1, 0 by the uh, displacement matrix of the element in local coordinate system. Instead of u prime e, we could write REUE, and now we have this expression for the normal strain. And if we do the multiplication of this row matrix and rotation matrix, we have a row matrix of cosine and sine of theta. At the end, we have expression for the strain based on the element nodal displacement matrix in global coordinate system. So normal strain can be achieved by the multiplication of BE matrix and UE matrix, where BE matrix is called strain displacement matrix, is equal to 1 divided by L, LE length of the element, times a row matrix of minus cosine, minus sine, cosine, and sine of theta E. After that, we could find normal stress by using the definition of Hooke's law. And here is the equation for finding normal stress. Sigma is equal to EE times PE multiplied by UE. Now we want to solve an example to show how we could use the strain displacement matrix. In this example, we refer to example 4.1, and we want to compute the strain and stress in the diagonal member using the obtained solution. This is the truss we have analyzed in the previous example, and we want to find strain and stress in this diagonal member. Since the main part of the solution was carried out in example 4.1, we only need to perform post-processing using the obtained results. Using the computed displacement, we could find the displacement matrix for element number 2. For element number 2, node 1 and 2 of this element are associated with node number 3 and number 2 in global node numbers. So here we have the displacement matrix for element number 2. Now we want to compute the strain. For finding the strain, we could use this equation. Epsilon is equal to uh, the matrix BE multiplied by matrix UE. Matrix B is strain displacement matrix for the element. For element number 2, the length is 5L, theta is equal to 150, and we could compute cosine and sine of theta, and at the end the strain displacement matrix for the element number 2, and after that we could multiply the matrix B for element number 2 by the matrix displacement in the global coordinate system to find the strain in element number 2, which is equal to 2p divided by AE. And after that, we could compute stress. Stress can be achieved by this equation. Sigma is equal to E BEUE. We have computed BEUE, which is a strain, and just we need to multiply uh, that amount by elastic modulus of E for the element, and at the end here we have the normal strain for element number 2, which is 2p divided by a. Finally, we have two exercises for you. Exercise 4.1. Consider the planar truss shown below and compute the displacement, reactions, and stresses in the element. You can solve the problem parametrically or using the values of A is equal to 500 square millimeters, E is equal to 2 times 10 to the power of 5 megapascal, L is equal to 1000 millimeter, and F is equal to 5 kilonewton. In exercise 4.2, consider the braced frame shown below and determine its lateral stiffness. The horizontal member is assumed to be rigid. You can leave your final answer in the comment. Also, I would like to mention that the follow-up videos will be posted. Thank you.